Magnetism is really important on the sun, and in this video we're going to talk about why. So as you know, the sun has sunspots, these dark blotches on the sun, and these are spots on the photosphere of the sun, or slightly above, where the gases are just a few hundred to a few thousand degrees cooler than the surrounding material. So the sunspots are actually glowing. They are just not glowing as brightly as the surrounding photosphere. So they appear in silhouette against the photosphere. And some years there are lots of sunspots, and some years there are few sunspots. And there's this cycle of 11 years where you get lots and lots of sunspots and then few, and then it repeats. And so these two images are showing you this from the year 2000, just a typical day in 2000, and then a typical day in 2009 at the minimum of the cycle. Sunspots, here's just a close-up picture of sunspots with the Earth for scale. The granulation, you see the surrounding photosphere, is it looks like you're looking at a bowl of sugar almost. And what you're seeing there is actually the convective cell. Remember, the photosphere is just the top surface of the convective zone in the sun. And it's just where the photosphere is just where the gas becomes transparent and the light can escape out into space. And so you're actually looking at convective cells of the convective zone, and that's these granulations. And each one of these is about 1,000 kilometers across, Texas size. And again, just to give you a sense of scale here, one of these little things, one of these little blobs, is the size of Texas. Okay, so the sunspots cycle, already mentioned that. You get highs and lows, lots of sunspots on a typical day, and then few sunspots on a typical day in this 11-year cycle. Now, this was noticed, after the invention of the telescope. There were a couple cycles that were observed, but pretty soon, 1650-ish or so, we went into what's called the Maunder minimum. Now, this is trivia. I'm not going to quiz you on the Maunder minimum, but right after the invention of the telescope, within a couple decades, there was this gap where there were hardly any sunspots at all. And that was kind of weird, but then it picked up after that, and it's been pretty consistent, although the sunspot cycle recently has been decreasing in intensity. But anyway, that is the sunspot cycle. Every 11 years, the number of sunspots go up and down. Now, something else happens with that. This is a graph showing the vertical axis is latitude on the sun, and the horizontal axis is date, going from 1975 to the present almost. And each of these dots on here, now they're really, really small, is representing a sunspot. And if you plot the sunspots, just their latitude on the sun, over time, what you find is in this 11-year cycle, so we're going from here, what's that, like 1977 or so, to over here, 1988 is when it starts the next cycle. So there are lots and lots of sunspots, and then you got a couple-year period here where there are very few sunspots before all of a sudden sunspots appear again. But notice also what happens. You get at the start of the solar cycle, you get the sunspots tend to be at sort of these mid-latitudes on the sun. As the solar cycle progresses, they go down to closer and closer to the equator. And then they disappear for the minimum time, and then all of a sudden the cycle starts over again with lots of sunspots near the mid-latitudes. So that's just an interesting feature of the sunspot cycle. And then the other thing I want you to notice here on this plot is the yellow and blue. So the yellow and blue has to do with the polarity of the magnetic field. Is it the North Pole up or North Pole down? The orientation of the magnetic field of the sunspots. And notice that it's yellow here, blue here, and then blue here and yellow here. And The and so the magnetic polarity. So the sunspots have magnetic fields associated with them, and so the full cycle of the sunspot is about 22 years, going from the start of one cycle all the way over to, with yellow on the top here, to the next time yellow is on the top. And so as I've alluded to, sunspots are tied in with the magnetic field of the sun. And so this is called a magnetogram. And we can actually make these measurements of the magnetic field of the sun from the Earth. That's kind of cool. It uses spectroscopy and something called the Zeeman effect. And that's getting into the details. But this was a day in 2016 when there were a fair number of sunspots. And this is a day later in 2016 when it was a day when there really weren't sunspots on the sun. And so here is this. This is actually a picture I showed you before, and that's sort of our introductory overview to the sun, where we had these are actually images here, but then the image is going to stop here and become an animation where we kind of peel away the sun and we look inside, and these are magnetic lines, magnetic fields inside the sun. So just like in the Earth's magnetic field is created by electrical currents inside the conductive core of the Earth. And so electrical currents create magnetic fields. Well, what we have inside the sun is we have conductive material, plasma. Now it's not molten iron and nickel like in the core of the Earth, but it is ionized hydrogen and helium. And it is conductive, so you can have charged particles moving, and charged particles moving is an electrical current, and that will create magnetic fields. But the magnetic field of the sun is much, much more chaotic, because you have, in that convective zone, you have lots of churning, and it's not like all the material is going in one direction. There is turbulence. And so the magnetic field that results from that more chaotic motion creates a more chaotic magnetic field. Now, overall, the sun has this magnetic field that kind of looks like the magnetic field of like a bar magnet, but yet superimposed on it also is this more random magnetic field, and it almost looks like an old 1970s shag carpet. And so the magnetic field lines there are much more chaotic, much more jumbled than in the case of the Earth. And so these loops that we have here, when you see a solar flare or solar prominence, this big shooting jet out, that is the gas eruption from the surface of the sun, and that plasma is actually following the magnetic field line. So when you see a solar flare or a solar prominence, and it looks like it's doing one of these loops, that's because it is literally following the magnetic field lines. So that's a quick overview of magnetic fields on the sun, and we will continue with other solar topics in other videos.